So this is example number 1 for equations of motion. For equations of motion, let's consider a flow with a property A that varies with space and time, and this property is given by this expression, and is moving along a fluid a flow that has a velocity field given as such, where A, B, C, and D are constant, R, theta, and Z are cylindrical coordinates quantities. And what you asked in the problem is let's find the rate of change of A seen by the the fluid particle of the flow, and also find the rate change of the velocity seen by the particles. So you can pause, you can take you can and write all this. So let's get start this. And when you do this problem, you know that as we talked in the lecture, that the partial of any quantity respect to time of the particle, rate change of any particle is actually equal to the substantial derivative of that quantity. And this is the expression that we have, right? Plus the time derivative of that quantity itself. In this particular example, A was a scalar, so it's all, it's straightforward. It just becomes this expression that we have here. So in the next chart, what we're going to start to do is we're going to work this expression. Since this is a scalar, then what I can do is this is the same as finding the gradient of this first and then doing this. If this was not a scalar, then I have to do the dot product first and then do this. But it really doesn't matter. I could do this first and then apply the rule. It will still give you the same answer. Okay. You got two options, but if it's a vector, you don't have option. You have to go the other way around. So just a refresher, this was the divergence. This was the gradient operator for in cylindrical coordinates. We talked about that. So this is, remember what I'm trying to do. And so if I did this in cylindrical coordinates, where A was equal to this quantity and B was equal to this, that comes from the previous problem, then you can see that V dot, so this, taking this dot this would give you this dot this gives you 1, so this is gives you this expression. You take this dot this gives you the second expression. And this dot this gives you the third expression. So if you just take the partial of A respect to R, this comes from this expression right here, then this will be d theta z times t. This is dr z t, dr z theta t. Okay, so now we put it all together. Again, we are just repeating what we did previously. And the partial of A respect to time, this is dr dr theta z. So the time goes away because they're taking a linear derivative of that. And then the substantial derivative that's equal to this, I put all the terms together, this is what I get. So I found what I'm asking for, part A. Okay, now part B is a little bit more trickier because in part B, now I want to find what happens at the what happens to the rate change of a vector of the particle, and that would give you the substantial derivative of the speed of the velocity, and I express all this as follows. Okay, this term is easy, and you can show to yourself the only thing that's left is 2 times c times t. Easy, because the other terms don't have any velocity term. Okay, so now the first thing I want to do is, in this particular problem, because it's a vector, you want to take this first and then apply this, the vector notation. This is the first term I want to do, and then I will deal with this part. So if I did that, what you can see is that V dot the gradient in cylindrical coordinates for our particular problem only will give you partial of r bz cosine of theta r partial of z plus zt squared partial of z. Okay, now you're gonna, so this is expression that I have here. Okay, so I'm going to take some space, and now you want to apply to whole thing velocity. This is velocity, this is the velocity, and this is the velocity. Okay, so that means now I need to find what each one of those velocity coefficients actually are, and I'm going to do that in the next slide. So partial of v respect to r gives you a sine of theta er. Also, you have to know that in this particular problem, you're also going to have the derivative of this respect to theta. Okay, gives you e theta. And then you also have derivative of e theta respect to time, theta gives you minus er. Then partial of v respect to theta gives you ar cosine of theta er plus ar sine of theta e theta partial of this respect to theta minus b times z sine of theta e theta, and then you have bz cosine of theta partial of e theta respect to theta, and then these terms I just evaluated them there. They will come back inside here. Then you find the whole expression of v respect to theta gives you ar cosine of theta minus bz cosine of theta er plus ar sine of theta minus bz sine of theta e theta. This goes here. Then the other derivative that you need is this respect to z gives you b cosine of theta respect to z. Okay, so now I got all these derivatives because remember when I did this problem, I needed this derivative, I needed this derivative, I needed this derivative. I got those three. You can see I got it here, here, and here. So I can plug this back inside these quantities, and I can do some math here, and you can show to yourself that you get the following expression. This respect to time will be a squared r sine squared plus a b z cosine of theta minus b squared z squared r cosine squared theta. There's a squared missing here. er plus bct squared cosine of theta plus abz cosine of theta sine of theta minus b squared z squared r cosine of theta sine of theta e theta plus 2ct ez, and that would be the velocity expression that we are looking for. So this is how these problems really work. Is kind of a summary of our what we did in the past and what we are doing now.